Dr. D here, and today we're going to learn about titrations, how you set one up, what to expect while doing an experiment, see titration curves, and deduce what you can learn from them. So let's dive into it in Content with Content. So to first set up a titration, you'll normally use a burette, and you'll fill that with your titrant. So this is either going to be a strong base or a strong acid. For this example, we're going to be using a strong base. And then in your flask, normally you'll put in the thing you're interested in looking at, your analyte. And this will be opposite to whatever you're titrating with. So since we have a base, we can only look at acids. And this can be either a strong acid or a weak acid. For now, we're going to be using a strong acid. And then you also need to add an indicator. Now, when you're choosing your indicator, you need to make sure that it's going to have a visual change at the desired pH when your moles of titrant are equal to the stoichiometric moles of your analyte. All right, so since we have a strong base and a strong acid come together, they're going to be equivalent around a pH of 7. So we need to choose an indicator around this region. So for this one, we'll be using bromothiamyl blue. So once we have everything set up, we're going to start adding our titrant by turning the valve. And while we're doing this, we need to also be mixing our analyte with our newly added titrant. So you can do this by either gently swirling the Erlenmeyer flask, or you can use a magnetic stir bar. And eventually we're going to see a color change. All right, now it needs to persist for a little bit of time, normally several seconds, or it needs to persist indefinitely but be a faint color or a faint change. And this will mark your endpoint. And we can go ahead and stop the titration by closing off the valve. So let's go ahead and do a little example here where we're going to have, for our titrant, 0.1 molar sodium hydroxide. And then for our analyte, we're going to use 50 milliliters of nitric acid. And we don't know the concentration of it, and this is actually what we're going to try to figure out. So we want to determine the concentration of nitric acid. So we can go ahead and start our titration by adding some titrant, and eventually we're going to see a color change, at which point we're going to stop titrating. And then we can go and look at our burette and get our final measurement and figure out how much titrant we added. So in this case, we're going to add 40 milliliters of sodium hydroxide. So we can work through a little bit of the math here. And one important thing to note is that at the endpoint, when we see our color change, hopefully this is equal to our equivalence point, provided we picked a good indicator. The equivalence point is when our moles of titrant are equal to our stoichiometric moles of analyte. So we can write down an equation where we have our sodium hydroxide plus our nitric acid. This is going to form water and the correlating salt. And with that, we can do some stoichiometry. So we start off with 40 milliliters of our titrant. We want to convert that into liters, so we'll divide it by 1,000, and it will convert this into liters of titrant. Then for every liter of our titrant, since we know the concentration, we know it's going to be 0.100 moles of sodium hydroxide. Then we can use our chemical equation, and we see that we have a 1-to-1 ratio, 1 mole of sodium hydroxide for every 1 mole of nitric acid. And now we can convert to our desired unit. So we're trying to figure out concentration, which would be molarity, or moles per liter. So we already figured out how many moles of nitric acid we have, but now we need to figure out what volume that is in. So I'm going to go ahead and say we're going to divide by 1 liter of analyte. And for every 1 liter of analyte, we have 1,000 milliliters. And then we can divide it by the actual volume that we started out with, which was 50 milliliters of our analyte. So now we can multiply everything on top and divide by everything on bottom, and that'll give us our answer of 0.0800 molar nitric acid, or HNO3. We can also set up our experiment in a slightly different way. So instead of using an indicator, we could use a pH probe. And pretty much this whole entire step is the exact same, but you'll be recording the pH at various spots of volume of your titrant. So we can actually set up a graph here where we're looking at pH versus volume of titrant, and we'll get this S-shaped curve. And at this very sharp incline, where it's very vertical, there's going to be an inflection point. And at that inflection point is where the equivalence point is, where our moles of titrant are going to be equal to our stoichiometric moles of analyte. And so then we could go through and do the exact same math we just completed. So to take a little bit better look at this, let's go ahead and look at a different example where, in this case, we're going to be looking at a weak base as our analyte. So we need to make sure we're using a strong acid for our titrant, and then we can measure the pH as we're doing the experiment. And you'll notice that we essentially have a inverse of our S shape earlier, because now we're using a acid titrant. But you also notice that the curve is a bit more gradual. And this is because this is looking at a weak base. All right. So whenever you're titrating, you always want to make sure you're titrating with either a strong acid or a weak base, or sorry, strong acid or a strong base, so you can get out a good number. But the other thing that we'll also notice is that our sharp incline, or sharp decline in this case, is much, much smaller. So our range is a bit smaller on where we can actually see the equivalence point. But at that inflection point is still the equivalence point. And one other bit of information we can find out is at 1/2 of the volume of the equivalence point, the pH there is going to be equal to the pKa of our analyte. So we get a little bit more information. So let's go ahead and go through some of the math here. And so we can say that we find out that our equivalence point is at 59.5 milliliters. We can write down our chemical equation where we have our acid plus base. And then we can figure out what the original concentration of our ammonia is, our NH3. So we're going to start off with 59.5 milliliters of our titrant, convert that into liters by dividing by 1,000. Then we can convert that to moles by multiplying by our concentration of our titrant. Looking at the equation, we can see it's a 1-to-1 ratio still. So it's 1 mole of HCl to 1 mole of NH3. And now we need to figure out our volume of our analyte. So we're going to essentially multiply by 1,000 to convert it into milliliters. And then we're going to divide it by the actual volume of 35.00 milliliters of our analyte. We can multiply everything on top, divide by everything on bottom, and we end up with 0.1700 molar NH3. Now we can actually answer another question of what is the Kb value of NH3. So if we look at 1/2 of the volume of the equivalence point, we know that's going to be equal to the pKa value. So the pH at 29.75 milliliters is 9.25, and we know that's going to be equal to our pKa. All right. Then we can use the formula of pKa plus pKb is equal to 14. This is essentially derived from the equilibrium constant of water being 10 to the negative 14. Then we can rearrange, so we can subtract pKa from both sides, and we'll get 14 minus pKa. When we actually plug in our 9.25, we see that our pKb value is 4.75. Now we can substitute in negative log for that p of the pKb, and we'll have negative log of Kb is equal to 4.75. we can bring the negative sign over. So log of KB is equal to negative 4.75. And then if we do 10 raised to both sides, we can get rid of that log. So 10 raised to the log of KB is going to be KB, and we'll have 10 raised to the negative 4.75. Then we can put that into, we can calculate what that should be, and we'll get KB is equal to 1.778 times 10 to the negative 5. And so we can figure out what the KB value is. And this is generally how Ka and KB values are figured out. But that's all I have for you today. So hopefully you feel a little bit more confident going into doing any kind of titrations and those experiments, and you have a little bit better understanding of what you can learn from doing a titration. So, as always, keep thinking, and I'll see you next time. Goodbye!